Okay. Okay. So this is the normal thread and hold on. So there is a piece here. And then so if you are asked to find the shear stress at a peak, so what we let's say that we use if you are asked to find the shear stress at the peak, what we do, what is it? At the APR, and the shear stress is equal to over so what's your answer? Yes, pretty bad. Do you use FOD? Okay. Or FOD it's shear stress. Yeah. FOD correct. Yeah. Should be FOD times correct. Which is the area of the So if you look at here, the pin, the shear stress is going to be like this. Is acting on the surface of the pin. So it's going to be a very easy surface. How about if we say bearing stress? If the question is asking you the bearing stress for this one. Cross section, so what would be the y? Yeah. So it's more times thickness is greater than the so bearing stress. Over 2R where 2 is the thickness. Okay. So for chapter 1, there's just only these two equations, which is only shear stress and normal stress. Bearing stress is actually kind of normal stress. This is in the effect. So what is question? So what would be the normal stress? You guys know where I live. Because there's two areas here. So there's a the series rate is going to add up. So we can do for the area, or you can do it calculate by divide the first into that's basically the everyone is just stress. The main thing you need to know is just like identify which area. So in chapter 2 we talk about green. And green, let's talk about green first. Demonstrate like this symbol, and just equal to work that out on your own, which is the change in length compared to the original length. So usually the question will have two kinds of string, which is formal string and the string used by force. So the total string will be and this is temperature per degree Celsius. Maybe one increase by 1 degree Celsius to the increase by temperature. And this string and temperature. And delta T is the change in temperature.
Like there was the flash and then the still up there at the top.
Oh, okay.
Yeah. Now I know.
Okay. And this one is just like there's this law, and so if you are given this so if you are given this question, what is the first action? If I'm doing this, I will look for the total rotation first. So, but in here, the string is only thermal string. Yes, there is no fault at here. So it will be alpha, which is and I'll get it will increase in length by 1 meter. So and here there is only 0.2 meter gap. So we can see this thing is going to increase all the way here, but pushed back by the wall. So if so next step you need to do is erase the wall and draw how it will look like. So the total length of the bar will be 3 meters long. But there is a wall here. Which here should be 1 meter minus 1 meter. The at first, this is still right there. This, and this. So the it only allows increase in length for 0.2 meters. So what we need to do now is calculate the stress in here fueled by the wall. So you guys know how to do this. Okay. Now you know it's going to increase by 1 meter, but you are only allowed to increase by 0.2 meters. So you draw the whole line, which is 3 meters here, and you are going to calculate the force done by the wall. So we'll use this equation, which is so you got the length now, because now you are considering a new question, which is the old length, and you're pushing for 8 meters. So the L is going to be 3 meters. This is the L. And the F, you're going to find that. And E is usually given by the question, so. And A, let's say this is, it's 1 meter squared. 1 meter squared. And now you are pushing it back for 0.8 meter, right? So the delta here is going to be 0.8. So with this, you are able to calculate the force done by the wall, and you are able to calculate the stress done by the wall by assuming that force.
Once you get the force, what were we trying to find here?
We're trying to find, maybe he's asking you for the stress in the bar.
Okay, so the force to find the stress.
Yeah, that's a good idea.
Yeah, okay.
So what if the question is now? So if the question is now delta T let's say, so this you can calculate the elongation was 2, which is 0.2. So that means that this bar is going to be elongated all the way here. But the wall is not going to push the bar back because the gap is big enough for the elongation. So there will be no force done by the wall to the bar. So that's why first we need to calculate the total elongation. This is for the normal trade, and we'll go to shear trade. So we are now going to chapter 2 review, and shear trade basically is there in the box here, and I give a shear force, means I push a force, push a box in this way, and it will be torn really close. And the angle you change here, this is going to be the shear strength. So the shear strength is an 11.2 right here. There is two shear. And this box equal so the shear strength in total will be just summing them together. Depends on how small the angle is. Do you have a question? So do you think that when do you use anybody get So basically there's chapter 2 and the number of chapter 3. Okay, in chapter 3 is introducing you this and you guys know what is in book, the sector. So if the person is giving you this one, you should be able to follow it by giving this one. So, okay, let's say Like here you are given the building stress and building stress. You will be able to find it. Building stress is this point. Before this is the activity. So we will yeah. Yeah, you're right. Should look like this because as you can see here, the E is going to be that. We will take to find the E is going to be this point. I'll use this point and this point. So E will take unit stress minus this point, which is 0, and the building stress minus 0. Like here you will the modulus of force. So here you cannot use any point beyond the building stress and building strain here. It's not a straight line. And here there is this is somewhere here, and we got shear stress. This is shear stress, this is shear stress, and this is and there is one more thing that anyone still remember what it is? Okay. Okay, yeah. So there is one bar here, and I put my suicide after. So if I put it at two sides, it will become a it will get longer in the length, but it will get shorter in the height. So let's say 30 cm, and then so the final ratio will be this is going to be this part, which is 8 cm minus 6 cm over by, this is the delta L, over by 6 cm, where the longitudinal strain will be 12 cm minus 10 cm over 10 cm. So this one is equal to the change in here, which is over the original reaction, which is 6. And we will get a negative number here because this is getting shorter. So in this equation, there is a negative sign here. And the poison ratio as an equation that relates T to C. T is equal to over poison ratio. So this is a poison ratio, and this is the G is always this one. So that's basically all 2 chapters. And those are all the equations for the 2 chapters. And now we'll go through some basic questions that for those.
Is that all the between 4 and 5.
4 is not clear, and
Oh,
yeah. But first time console, I didn't mean to.
yeah.
It's not basically. Yeah, I mean, hold on. Yeah. Chicken boy is this. Yeah, yeah. I'm not sure about chicken pie. Chicken pie is basically just like after everything from sugar one to two. It's like using a technique for sugar one to two. And we go to so for this question, there will basically be at least 3 cases. So the first case is there's 2 plates here, and there is bar 1 and bar 2. So if there is a compression force here, what will be the relation between reading 1 and equal to the rest of it? Because there is a plate here, the plate is going to stick to bar 1 and bar 2, so how much bar 1 compressed is going to be equal to how much bar 2 compressed. So this is for when you have a circular even though there is no plate that actually takes the this, but when you see the circular part and there is a force here, the green one is and you have to use this on your homework section 1. So there is 3 bars here. Then this tool has the same material and the same design. So when I apply a force in the middle, this thing is going to be open. So this means that the middle one is going to be this only apply that this tool is the same material and has the same length. So it won't like going this way or this way, it just comes down to that. Got it? This is only applied when these two have the same material and the same length, and the force is in the middle. And we will put it there. If this tool has a different length and different material, you cannot say it will be formed like this. So it might look like this. Which is so we can only use this when the assumption when this is and this has the same material and okay, that's basically case one communication. So what would be the relation between 1 and 2 for the one and two plus one plus two yeah. Yeah. Everybody? Because the only part they can that won't be yeah. So you can get through next slide. Force. Apply a force and power one. So what will you do? That's where you can get into and how much is increasing, right? Will change to how much is increasing. So, any questions in here?
This might not be a relevant question, but I'm wondering, like in the book, and they have pictures and it's like the little part is broken.
Oh, it just means that, right? Just show like, because maybe this is 10 meter and this is 1 meter. It just shows that this is not like, how do I say? Yeah, it's not in the same scale. That there's still a lot of between like, yeah. That's what it means.
Okay, like, I don't know if they're breaking.
Yeah, that's
Okay.
so we'll go to this page will use so that here now. So what one is one is big, and two is so I don't know who's right. So another thing, oh, that is so you see? Yeah. So it's going be the same, it's just a different sign. So, because as when I'm pulling this way, this thing will affect this way increasing length when I'm pulling it down, and this way increasing length. So the relation will be because this is the slow scaling speed. So if I'm pulling this way, this is increasing length. And this is pulling this way, and this is increasing length. So yeah. So it's possible that yes, we can also share about how the force is going on, but the thing we can share is one is going to increase while the other is but it should be one operation and one operation. But I think there is some problem with the opportunity set, and we'll go through this one. Okay, so this is a sample attempt to this one. And there is 3 questions. This is how it's going to look like for an exam. So let's go to question 1. So it's done like, I don't know how to do it. Capital is each one dollar. the inner part of this bar is fixed all the time. So it's fixed all the time. So how much this all the part is going to form is going to be significant. because the two cars are going to share the microphone. It's not like the microphone. You can read like F1 plus F2 is the microphone. You don't really get so when we have already moved to the SLP, so each prior you think they'll use
Yeah, but then people are at, but then you get the elevation, you like have that maybe, but then you don't have.
Right, that's what it is.
Yeah.
I like it for this. So in this question, the first thing you have to analyze is they are stick together. So I am how so since they are kind of like a car that we mentioned just now, they have this relation. Delta 1 equal to delta. And I can write it down to F1, L1 over V1, A1. Equal to F2, L2, V2, A2. So I got L1 and L2, which is the same for V2. And I got E1 and E2. For E1, let's say the outer part is 1, the inner part is 2. So the outer part, this is the E1. This is E1. And for the inner part is E2. Okay. So I got E1 slope and E2 slope. And A1 is very simple. So the outer part is 2 times 2 minus the inner part, which is 1 times 1. Is equal to 3 squared. This is the area of A1. While the A2 is just the inner part, 1 times 1 times 1. So I got this and this. So now I can have a ratio between F2. So now I only know a ratio. So I need one more equation. And as here you can see they share a force of F order form. So F1 plus F2 is equal to F order form. So now you got two equations and two on it. So it should be able to solve it. Are you confused at this part?
Well, so you're trying to abstract, right?
In here is they have the same elevation, so I come out with this. Are you okay?
Yeah. And again, when you get the voltage,
Yeah. In here you got L and E and A, so you'll get F1 equal to a number of F2.
okay, so then we're calculating the graph.
So when you're so after you get F1 and F2,
Yeah.
how are you going to calculate stress?
Yeah.
Yeah, the stress is just F over A. If you are calculating for stress one, it's F1 over A1.
Okay.
So it's F2,
That's what.
yeah.
And then is that calculate the elongation of the bar, how do we get that?
So it's just because they are going to be the same. You can either use this one or this one.
So you can calculate either one individually.
Yeah.
That makes sense. I don't know why I didn't think about that, but
Because that's how we started the session.
yeah.
Yeah. So somebody tried to do it like this. They started they got a different area and try to separate the pores into two pores by using the area, but that's not how the way to do it because you don't know how much pores is going to be on part one and how much pores is going to be part two. It's not like proportional to the area.
I guess I was wondering like which one you can calculate the elongation, but it doesn't matter.
Oh.
So so I get it.
Okay.
Yeah.
So for this one, for question 2 is about torque. I'm not sure this is going to be in your exam, but question 3 you should be able to solve it because it's about Poisson ratio that we talked about just now. This is like a 3D. This is a steel weight and have a thickness of 1 inch. So now the change is when there is like so when I have a pause here, pause here, pause here, pause here, this thing is going to be better, right? I'm holding that pause. And this part, which is the thickness, is going to be smaller. So this is it's just using a Poisson ratio in a bit different way. Because you now have 2 threads. Okay. Yeah, I think that's it. And for the example 1, okay. So here, there's 3 samples, but the sample 3 is not working. Okay. So for sample 1, there is a lot of question in there, and the solution is given. Yeah, but try not to look at the solution while you are solving because it looks so easy when you are looking at the solution.
Yeah.
Yeah, right. So there is a lot of it, but you should, if torque is not included in your exam, so basically you just need to go through till question 8. This is for the whole semester, this sample exam. For the whole semester. So basically for chapter 1 to 5 or 3, it's going to until question 8. If you are able to solve this, then without looking at the answer, I think you can get a for this. Because this is kind of like private in the midterm. So how to prepare for the midterm is that then I do this and the sample exam and I choose like 10 questions for chapter from the next group and and then like 2 weeks after
It's like 1.5 weeks.
Okay. Okay, that's it for today.